I'm the technical director here at Team. I previously was a thermal design authority for a defence company called GC Marconi. I've had 30 years experience with CFD and FE packages, and I've used it in a wide variety of industries. Team Engineering was formed in 1997. We've been a Siemens business partner since then. We became a mentor business partner last year, 2017, and that was then purchased by Siemens. So now Mentor is part of the Siemens portfolio. Siemens paid $4 billion for Mentor Graphics. Team have got two offices, one in Lanarkshire and our technical office, which is down in Huntingdon. We do all of the Siemens portfolio, but we also assist the development teams by attending and working on beta tests. So we do the CE beta test, the design, we've done team center beta tests, we've done pretty much all of the portfolio beta tests for Siemens over the last 15, 20 years. We can do Siemens certified courses, or more importantly, we can do bespoke courses to your requirements, because sometimes our customers want to go into a lot more detail than the training material that you would get from just a standard course. We also do installation, configuration and customization, and occasionally we do consultative services where we do jobs for companies on a as required basis. Today we're going to look at the mechanical analysis division software from Mentor Graphics. Within that portfolio, there's a 1D simulation tool where you can do schematics of cooling systems, hydraulic systems, etc. And that's a product called FlowMaster. You've got Tester Terra LD, which is a tool which characterizes components for you thermally, and then they can be reused. So that's a measurement system. And then for packaging electronics, there's two solutions there, which are FlowTherm, which a lot of people may well have heard about. It's been around 20, 30 years. And there's a product called FlowTherm XT, which is an extension to that to handle more regular geometry. What we're going to focus on today is the FloEFD product. So that will allow us to do a wide variety of CFD problems, going from just generic conduction cooling, engine blocks, turbochargers, lighting, etc. And we'll see that as we go through the presentation. So we're going to focus today on FloEFD. And all of these systems, as you can see with the blue arrows, can be linked together. So the outputs from the measurement system can be put into FloEFD, and the outputs from FloEFD can be linked into the 1D simulation. So they're all linked together. As Chris mentioned, we're going to sort of discuss what makes FloEFD different and why it's really come about as a product. The main reason for it is that it's very designer focused. So it works in the CAD design space environment, which makes it very easy for designers to optimize their designs from a CFD perspective before they then either pass it on to a specialist group to do certification, or a test group who might go away, do some simulation, and then you feed that information back into your analysis model. So it's very CAD centric, CAD focused, and that's what we would call front loading, where we try and do the simulation at the front end of design rather than waiting until the back end once it's designed, and it's harder to and more costly to make changes. So we try and do everything at the front end. So that's what front loading is referring to. One of the strengths of a front-loading solution is that you have it in your native CAD environment. So if you do your design in CATIA, then you would like to CATIA. So as you do your designs, you can modify your designs and then redo your CFD. It's all embedded in the same familiar environment. We also have it for Pro Engineer, Creo, for NX, and for Solid Edge. And when you're in these different tools, the interface for FloEFD is the same. You're just working in your own native geometry creation environment. FloEFD was born in aerospace in Russia in the 80s. So at that time, when they were doing development of missiles and other things as part of the Cold War, They didn't have high-powered computers, so what they had to do was produce a CFD code that they could solve on the limited hardware, but still get accurate answers that they could compete with the US at the time. So the first commercial version of this code came out in 1991. So FloEFD has been around a very long time, and it's got a lot of techniques and technologies within it that makes it very powerful, very quick, and very accurate. FloEFD uses a combination of numerical, analytical, and empirical methods. So it uses Navier-Stokes. It uses some empirical formulae to calculate hydraulic resistances, heat transfer, and a few other parameters that I might want to use in its simulation. And it also has the ability to put these two bits of knowledge together. So it means you can have fewer cells, but you still maintain the accuracy by using a combination of these techniques. When you have some very complex geometry, one of the approaches you used to have to do in CFD is you used to have to defeature it, get rid of a lot of the features so you could then mesh it very effectively, or you have to create fluid volumes, and you have to really do a lot of work and manipulation to get the fluid volume, get the structure, control the mesh between them. Where within FloEFD, they have a concept of smart cells. So to the right of the blade, you can see one cell, but within that cell, it's got several control volumes. It's got control volumes for fluid and control volumes for solid, and it allows you to simulate the designs with a lot less cells, because the cells can contain many different kinds of control volumes, not just fluid or structure, which is what you would do in a traditional CFD system. So as a result of that, there's less simplification required on the geometry, less user input, and you need fewer cells to get a suitable runtime. When you're simulating in CFD, you may well have some effects that are boundary layer driven. Some of them, may be you're looking very tightly at how much heat is transferred through the boundary layer, or you're looking at how the boundary layer develops over a surface. And to do that, FloEFD recognizes areas where it needs to refine the mesh, and it'll put a refinement in, or in some cases it can do a crude mesh and then use an empirical formula to calculate the appropriate parameters between that or through that cell. So again, it makes it very easy for you to handle very complex geometry with a minimal amount of input from the user. So again, it lends itself towards easy use and automation. What we're going to do now is go through a few different slides, which are just really to try and explain where CFD applications can be applied. It can be applied in a wide range of situations. So in this particular case, you can look at clean rooms and labs. So you might want to look at how the airflow goes through the clean room. You might want to make sure you've got it at a stable temperature. You might well have some ducted networks. You've got classrooms with all your PCs and air conditioning units. You can have the data centers that you're trying to keep cool, looking at hospital wards. There's a lot of applications that we can apply within HVAC and within building applications. Within the electronics environment, a lot of that is down to electronics packaging. So we're looking to package electronics, select an appropriate heatsink, looking at gradients in PCBs and distribution of heat across a PCB. We might have a rack-mounted system where we're looking to see the airflow through the rack. We may well have some LEDs on the front panel. We might have heat pipes, what we're using to cool some bit of structure, like you might see in a laptop screen, which has got heat pipes taking it down into your chassis. So there's quite a lot of different kinds of simulation that can be performed in the electronics environment. If we're doing processes, then here we might be looking at gas burners, some combustion. We might be looking at some fans, some chimney approaches, stirring tanks, injection systems, particle separators, a whole load of different applications within the process industry. Even if we just take a domestic kitchen. Within that, you've got several different kinds of simulation that you may well need to perform, from the LED lights down to the radiator design, the dishwasher, where we're looking at how we flow and how we manipulate the environment to get yourself clean dishes out of it. Look at air conditioning units. Again, several applications that sit within that environment. In the aerospace environment, which is probably traditionally where all of the CFD was performed because of the nature of that environment being very technology-led. And there you can do aerodynamics over the structure, looking at heat exchangers, looking at internal lighting, looking at externally mounted pods, looking at cabin climate control to make sure you get a nice, stable, even environment for the passengers on the plane, etc. So again, in the aerospace environment, several applications it can be applied to. In motorsport, what we're looking to do here is potentially look at lift and drag on the car and try and optimize the performance. We might have heat exchangers that we're trying to package and maximize the extraction of heat, but we might want to put them in a very compact area of the car. Several other areas, looking at the wheel arches, how we define the airflow around barge boards, etc. Looking at engine manifolds, again, we can look at how effective we can make those parts of the structure. Previously, what we did is we did a webinar on a front wing analysis where we varied the front wing and then we looked at the lift or drag that we were getting onto the front wing. So that's available, and we'll be publishing it after this event if you didn't see that particular webinar. In just standard automotive applications, we can look at windshield wiper analysis, turbochargers, look at some valve design, some exterior aerodynamics, windshields, lighting, several areas, catalytic converters. So again, very, very wide and varied what we can simulate. And what I've put up here is just a case study that was used previously for the skeleton in terms of optimizing the aerodynamics on the skeleton to ensure that they could go down the track in the fastest way possible. So again, just something that was topical after the Winter Olympics that was just finished. So a wide variety of applications that it can be applied to. Okay. What we're going to do now is go through a demonstration of a floodlight, and this is going to give us an idea of what we need to do to perform a floodlight simulation and break it down into logical steps so you can see how each of those steps are performed. So if we're looking at conduction, here we've got our bulb or our lamp, and the lamp's made up of several different materials. So you've got the quartz bulb, you've got the pinch, you've got the lamp base, you've got the wire, and it's also filled with argon. So we need to simulate that part of the floodlight to get an accurate representation of how the heat conducts from the lamp out into this surrounding structure, the case of the floodlight. And here we've got 7 different materials that we want to apply. So it's, we've got quartz, we've got tungsten, alumina, molybdenum, we've got several different kinds of materials that we need to simulate and look at how they interact with one another. So as you can see here, we've got our lamp, then it goes out into a holder, and around the holder and the lamp, we've got a reflector, which is aluminium, so something that's relatively conductive, so we can get the heat away to the back of the case, so we can get rid of some of that heat to the outside world. And also, with it being a very polished reflector, we're also looking to simulate the radiation effects and see how that can be used to transfer heat out of the floodlight. So here, if you look at the overall, we can see rubber seals, the front glass, the rear case. I've removed the front case just so we can see what's going on. So this is what we're trying to simulate. As you can see, loads of different materials, loads of different volumes. So what I'm going to do, after I've defined my model, I'm going to also need to look at the airflow. So I've got external air that will go around our case and cover. We've got some internal air that's going to flow within the reflector and into any of these areas, so there may well be a leakage around to some of the back within the case. And then we've also got argon, which is internal in our lamp. So we've got several different fluids that we want to model, so we can look at the convection from our structure to the fluids. And what I'm going to show you is how we define those fluids and how we define that part of the problem. So first part is to do conduction and the convection and just show you how that's defined. So in this movie, what I'm going to first of all do is look at my general properties, look at the solids, and my default solid is aluminium. So if I don't tell it otherwise, it's aluminium. My default fluid is air. So all I need to do is tell the software anything that isn't those kind of materials. So I'm going to create a subfluid domain for the argon. So I define my gas. I pick one face inside the bulb. So here I'm just using a smart pick from my CAD system to pick an internal face. And then when I OK that is then argon. So if I right click on it and show it, as I rotate round, you can see it's automatically created the fluid between all of my CAD geometry. I didn't have to create the fluid volume myself. It does all that automatically. Everything else is getting created externally and internally automatically because the software is going to do that for me. So what I'm going to do now is define the conduction and the materials. So as we go in here, you can see I'm picking the quartz and defining where I want to put that. Then I'm going to insert other material properties. So in here, I'm going in and defining the alumina. But as you notice here, I'm only picking one side to put the alumina on because in this case, I'm only modeling half of it because the other half is symmetrical. So in this case, I'm only going to model half the set of boundary conditions. I'm choosing the lamp and setting that to be, the wire to be tungsten. And within FloEFD, you've got a very expansive engineering database, engineering library that you can reuse, or you can create your own particular parameters. So here I'm defining the molybdenum. And then I'm going to look to apply something to represent the seal, to the glass seal at the front. So here I'm just going through and choosing it. You notice at the bottom of the form it's got radiation transparency. So all of the materials I've chosen I've defined as being opaque. So my seal, everything that I've defined is going to be defined as opaque. So what I want to do now is I want to show you how I start and look at the radiation part of the problem, and then how I define the radiation properties. And some of those materials, or one of the materials, I'm going to have to change because I want the bulb and the front glass to be able to transmit radiation. I want it to go partially through it. Some of it will get absorbed. So I need to start and simulate that rather than making it opaque. So if we look at the radiation problem, we've got our tungsten source, which is at 2900 Kelvin. And it's going to be a diffusive source, but we could also have a directional collimated source if that was appropriate. As you can see, we've got the quartz glass, which is absorptive around it, which will absorb certain wavelengths depending on what our source is. And then we've got our polished reflector, where anything that hits it isn't absorbed, it's just reflected. So we need to start and define those parameters so that when we solve it, we get an accurate representation of the heat transfer within the floodlight. So if we look at that in detail, what I'm going to do now, because as I mentioned earlier on, I'm only doing half the problem, I can go in and start and define it. So here I'm picking up the quartz, I'm making it absorptive, I've got a refractive index there and what wavelengths it will transmit and what the emissivity is. Now I'm going in to start and define what volume source I'm putting in. So here I pick the wire and I define what temperature that wire is at. See, I'm saying 2900 Kelvin. I'm now going in to define the radiative source or radiative surfaces. So here I'm picking up polished aluminium and I'm going to pick the faces. And as I was saying, because I'm only modeling half the model, I don't need to pick all of the faces that I want to be polished. I only need to pick half of them. So I only pick the one on the right hand side, but not the left hand side. So once I've defined that radiative source, the next source that I want to define is a white wall, and that basically says that all incident radiation is reflected. And I'm just defining that on my tungsten, so everything is coming out from the tungsten. I'm also defining the kind of radiative source that I've got. As I mentioned earlier on, it's diffusive, so here I'm saying it's a diffusive source on where my tungsten is, give it a temperature, and also see what spectrum it's emitting. So again, I can create a custom spectrum or use an out-the-box one. So that's how I've defined the radiation part of the model. So I've defined my reflectors, I've defined the kind of radiation I've got and the kind of spectrum that I'm going to radiate. And I've also said whether things can reflect or whether they'll be absorbed. So the next phase is to take it through and do a solution and then do the post-process. So if I solve this, it's a very quick solve, 5-10 minutes or something like that. But what I'm going to do is take you through and start and look at the results. So in this case, I'm looking at the temperatures on the solid, so I can see the temperature of my tungsten, the temperature of my glass, the temperature that I'm getting. So what I'm going to do is take you in and show you how we start and post-process that and how simple it is to do within FloEFD. So once I've done my solution, and we want to look at the results, here it's already got some results in it. What happens is if you define certain results, every time you solve it, it recovers those sets of results. So here I'm going in and just looking at the temperature on all of these surfaces. As I mentioned, I only did half the model, but here I'm reflecting it so I can see it as a full representation, although I've only simulated one half. So here we can look at the temperatures in Kelvin that we're seeing. I'm adding on the housing that sits at the back, the case. So I can start and play around with what I have and what I've got hidden. If I go to the temperature bar, I can just drag them around and it then changes the display on the fly. So I can just simply drag them around and control what bands I want to look at. Here everything is in Kelvin, but I'm more interested probably in degrees C. So I'm just changing the units to be degrees C. So it means now when I go in, I get everything in degrees C and it's a little bit more relevant for what I'm looking at. Now again, I can start and drag and look, or I can just type in the value. So here we can start and see what temperatures we're getting on the housing. We can start and drag it and pull it around. So it's very easy to get in and see what you want. You can also see, go to, the maximum on the plot, minimum on the plot, etc. So here we can start and get a feel for how that is behaving thermally. So here I'm just putting it back to the plot maximum so we can see what we've got. I've got a cut plot which shows the temperature of the fluid that's going around and inside the organ and inside the floodlight. And again, what I can do with this is I can drag it around and start and get a feel for what the temperatures are. So here you can see how it's heating up the outside air that goes around the floodlight, and obviously internally you can see what temperature that's sitting at. But it gives you an idea of the plume that's getting formed around the floodlight. So again, very easy, very quick to do. What I'm going to do is put on some flow trajectories. So here I'm going to look at some streamlines that are going to flow around. So I want to see how the air is drawn in and flow and is took around my case. So here I pick a plane and then I get a streamline to show as it is drawn in and around my case. So you can see as the air is pulled in from the outside world, dragged over the top of my unit and then going out into ambient at the top. What I want to do is I want to look at the flow of air or internally and the organ within the bounds of the case. So here what I'm doing is I'm just copying it, picking a plane internally, and then I'm cropping the region to define where I'm interested. So in this case, I'm looking at velocity, I crop the region. So this is the region it's going to use. And then what I can do is I can just snap to a view and then drag where I want to look and which region I want to consider. So here I'm just dragging it in to control the region that I'm interested in, which is whatever sits within the case. Again, I'm just snapping to views and then pulling that in. Okay, so once I do that, it then calculates the flow and the streamline that sits within the housing. So now you can see what we've got within the housing. I'm just going to hide the case away and put the lamp assembly on so you can see how we've got the flow around the lamp internally, and we're looking inside the floodlight and give us a feel for how that works and the kind of distribution that we have there. And again, we can have multiple displays on top of each other here. What I'm going to do now is edit it and change it and display some velocity vector. So here we've got some sliders that you can just simply drag them around and just pull the slider. So when I created this video, I went a little bit excessive. So when you look at the display, you'll find it's very black because it's just full of vectors that are very, very small. So as we zoom in, we can see the vectors, but a little bit too excessive. So again, we can just edit it, go to the slider and just make those entities a little larger. So then we can see the flow internally. At the moment I've done them as black, but what I can do is I can get them to be colored by the velocity vectors. So what I can do is take it in and switch on that I'm interested in having the colors by velocity rather than black. And now as you can see the flow and how it's drawn in and it goes around that particular plane. And again, we can change the size of the vectors so we can sort of see the direction and other attributes a little bit easier. So here I'm just going to change them to be bigger arrows. But it gives you a flavor for how easy it is to do the post-processing. The last thing I'm going to switch on is I'm going to switch on the mesh so you can see what mesh was used to solve this problem. And I didn't do any meshing, as I mentioned earlier on. The software does all of that for me. So as I put the mesh on, switched on the boundary layer representation there rather than the mesh. So if I put the mesh on, now I can see the mesh that it's used. Areas where it's a little bit more refined, it's required to get a more accurate solution, so the software has automatically refined it where it needs to and left it crude in areas that it didn't need to do anything about it. You notice those cells are very large cells, and they cross the case, the inside air, the outside air. So as I mentioned earlier on, the smart cells handle all of the transfer in those particular regions between the control volume for the conduction model and also what you would get for the airflow and the fluid and the radiation. So it's a very, very quick way to simulate these kind of problems. What I'd like to do with the last slide is just give you a feel for other things we could have done with it. We could do condensation, evaporation, icing, de-icing, look at film thicknesses. So in this particular animation, we're starting with a certain thickness, and then as we illuminate it with the floodlight, it gradually melts away the thickness of film until we've got no film. So you can see the bit that's the other side of the rubber seal is sort of the last bit that gets warm enough to start and dissipate the film. So again, we can do some quite exotic cooling, evaporation, icing, de-icing, etc. So that was just really to give you a feel for what we could do with it if we decided to take it a little bit further. I think now we're at the point of question and answers. I'll just pass you back over to Chris.
Thanks very much, Mark. Right, we've got a couple of bugs here. Type in there. Is there a plugin module for FloEFD into Inventor? That's the one CAD package that we can't plug into, but in that solution we offer Solid Edge as a standalone. So you have Solid Edge with FloEFD. It's actually quite an economical way forward, and Solid Edge can read in Inventor models straight in, so it's not any hardship. Create the CAD in the Inventor, your package you're used to, read it into Solid Edge and run your FloEFD model there. All the other CAD packages have a FloEFD plugin. Can you do more detailed modeling on LEDs? Yes, you can go to quite a good level with just the package that Mark showed there, but we do have specialist modules that enhance your capability, and they're available for LED and also for HVAC. So I've got a note of you there, so your name, I will send you the brochure on LED. And licensing, so the license is very flexible. We do perpetual licenses with maintenance. We do annual licenses or term licenses, which can be 12, 24 or 36 months. And we do lease licenses, but we do have a minimum requirement of 3 months on those. So yeah, flexible options. You know, if you've got a short-term project, then just have a look at a lease with us. Is there any other questions coming in? Right, I think that's covered them. If anything else comes to mind, you've got an email address for us, so drop it in and we'll answer those questions. This video will be posted along with the Formula One airfoil that we did a few weeks ago, so you can have a look at those again, and please share them with your colleagues. So if there's no more questions, I will say thank you very much for your time, and thank you. Have a good afternoon. Take care now. Thanks. Bye-bye.